Başlattım. Merhabalar arkadaşlar. Hoş geldiniz dersimize. Nasılsınız? Umarım iyisinizdir. Abbas hocam şeyi anlatacak bugünkü konuyu. Ben de burada dinleyici olarak katılacağım. Sorularınız olursa cevap vermeye ikimiz beraber çalışırız. Teşekkür ederim katılımınız için. Hocam buyurun. Ben sesimi kapatıyorum hocam.
Teşekkür ederiz hocam giriş yaptığınız için.
Sağ olun.
Evet arkadaşlar, bugün hızlıca bir Türkçe giriş yapmış olayım. Sonrasında İngilizceye döneceğim. Geçen haftaki konumuz loop'lardı. Etiket belirliyorduk. Loop'u gönderiyorduk hatırlarsanız. Loop keyword'ümüz vardı. Label dediğimiz, etiket dediğimiz, sonrasında 2 nokta olan o satırdaki instruction'ı atlayan bir loop keyword'ümüz vardı. Kendisi CX'i otomatik azaltıyordu. CX kadar bir döngü oluşturmamızı sağlıyordu. Bu hafta CMP dediğimiz compare'ın kısaltması olan bir komutu göreceğiz ve JMP, jump'ları, atlama dediğimiz jump'ları göreceğiz. Hatırlarsanız size demiştim ki emülatörün help'ini açtığınız zaman bir sürü instruction var. Bu instruction'ların hepsini işleyeceğiz demiştim. Bugünkü dokümanda şurada gördüğünüz JA, JAE, JB bunların hepsi jump. Bundan bahsetmiştim size. Bu hafta bunların hepsini kapatmış gibi bir şey olacağız. Ben size diyeceğim ki kendinize uygun jump'ınızı seçin. Şimdi neyden bahsediyoruz? Mesela JA buradan başlayıp J'ler şuraya kadar şu grup jump. İşte iki çeşit jump var. Unconditional, conditional dediğimiz. Unconditional jump bir tane, JMP şu jump. Diğer hepsi conditional jump. Yani bir duruma göre atlayanlar ve ne olursa olsun atlayanlar diye ikiye ayrılıyor. Hızlıca böyle bir intro yapayım. Compare'ımızda karşılaştırma yapıyor. Bu karşılaştırma işlemini çıkarma işlemiyle yapıyor. Birinci operanttan ikinci operantı çıkarıp flag'leri set ediyor ve karşılaştırma yapıyor. Sonra biz o flag'lere bakarak atlayacağız mı, atlamayacağız mı, program nereden devam edecek diye karar vermeye çalışıyoruz. CMP'miz de bu. İşte unconditional jump'ımız da bu. Şimdi anlatacağım zaten onları. Onun dışında geçmişe yönelik şuradan gideyim. Move, add, sub bunları zaten sürekli kullanıyoruz. Increment, decrement, tek satırlık, tek değişkenli, tek parametreli instruction'lar. Bugün de göreceğimiz compare'la aslında karmaşık, kompleks programlar yazmaya başlayabileceğiz. Okay, let me switch into English. Okay, my friends, today's topics are compare and jumps. Before diving into compare, I'm going over and start from jump. This is unconditional jump. Unconditional means it didn't look anything, it just jump. So let me first open the help, go to instruction set and go over to unconditional jump JMP. Okay, JMP. It takes one parameter. It can be label or it can be directly address, forward address. We generally use label because it's very easy. Forward address is very hard to determine. So know that we only use label for this case. Okay, what is unconditional jump? Unconditional jump transfer control to another part of the program. Let me copy this example from here. As you can see, algorithm is always jump to that label. This is an example. We don't use this include libraries or organization 100H. Never mind about those two lines. Okay, it puts some value into AL. It jumps to label 1. Label 1 is here. Let me emulate this one. As I said, never mind the first two line. By the way, if you use organization 100H, data segment becomes 700. That's why data segment saying 700 here. It's not important. We are not using that. Okay, we put 5 into AL, and now we are at the jump instruction. This is unconditional jumps, and it is going to jump over the label. Which label? Label 1. Label 1 is here. It will go over and print this line. Let me emulate this here. As you can see, it's printing out the got here. It didn't appear print out not jump. Let's change this code. How can we change this? We can comment out this section. Yep, we can comment out this section. If there is no print, it will print not jumped. And later also got here. Okay. With this example, you can also see that you can use print function to print strings to the screen. Okay, I'm going to write my own code. This is a bit complicated. I'm going to put 5 in AL, increment AL. Let's put label in here, which is Abbas. Okay, move CL 7 JMP Abbas and red. Let's move this out of this loop. Increment CL. Okay, I emulate the screen. It put 5 in AL, 7 in CL, as you can see. Now I'm in the loop, let me say. It increments AL, decrement CL. They are now 6, 6. JMP, which is JMP, which is unconditional jump. So it didn't look anything, it just jumps. So it jumps into label, which is Abbas, and increment AL, decrement CL, increment AL, decrement CL. It will run endlessly. Because JMP is unconditional jump, it updates instruction pointer with the label. Okay. Unconditional jump, the easiest one. We are going to use unconditional jump in order to create an endless loop. For example, this is endless loop with some different codes within this endless loop. We can exit out from this loop. We are going to cover this in this session. So unconditional jump is this. Let's go over and start from a jump, for example, JE, which means short jump if first operand is equal to second operand, as set by JMP instruction. Just never mind this explanation. It's a short jump. It looks for the 0 flag. If 0 flag is 1, then jump. I turn back in here and update this JMP into GE. I'm going to make a indentation so that you can understand this. This is in the loop. Okay. And I'm going over to increment and decrement instruction. For example, decrement. Decrement instruction can change the zero flag. As you can see, it can change relative to case. Change the zero flag. Decrement is the last instruction before jump equal. So decrement can change the flags and jump equal. Look at those flags. Let's emulate this one with opening flags. I want you to be careful about this zero flag. Zero flag is now 0. 0 means there is no 0 result. 1 means there is one 0 result. For example, decrement CL. When CL becomes 0, it means zero flags will set to 1. Okay, we will wait CL to become 0. Yep. Let's run over increment, decrement. Oops. Yep. It finished. Why? Because we use jump equal. We said that if the zero flag is 1, it will jump. It didn't jump because zero flag is 0. At this point, it looked at the zero flag, which is 0, and didn't jump. It finished the program. Let's change this jump into more meaningful one, which is jump not equal. The opposite version of jump equal. It looks at the zero flag. If zero flag is 0, then jump. Jump not equal. Update the code like this, so that it will look at the CL value. When CL becomes 0, decrement instruction update the zero flag. Zero flag becomes 1, and jump not equal becomes meaningless at that time. But for now, it will run till zero flag becomes 1. Let me reload this program and run this a little slower. Not faster, slower. Okay, flags. Look at the zero flag and CL. CL is 0, zero flags becomes 1, and it didn't jump. I'm going to reload this one and go one by one. AL is 5, CL is 7. Decrement CL, CL becomes 6. 6 is not 0, so it didn't set the zero flag. Jump. Increment AL, decrement CL, there isn't anything that becomes 0, so it didn't set the zero flag, so it didn't go over and jump. It goes like that. CL is 3, CL is 2, CL is 1. At this position, right at this position, decrement CL will decrease the CL by 1, so that zero flag becomes 1. And when zero flag 1, this jump not equal, as instruction said, not jump. It was jumping because zero flag was 0. Now zero flag is 1. It is not going to jump, and the program finished. Okay. I'm stopping in here and asking if there is any question about this topic. Is there any question about flags and jumps? Sorusu olan var mı arkadaşlar? Şu an araya girip sorabilir. Yok. Tamam. Okay. Let's go over and look at something different. Not jump not equal, but let's say JA. JA. It means jump above. It will look at the instruction And that instruction, if the first operand is greater than second operand, it will jump. But how do you understand that first operand is greater than second operand? With the flags. If the char flag is 0 and 0 flag is 0, then this JA jumps. So I'm going to update this code with JA. Why? Because I know that no operation, increment or decrement, we're not going to update the char flag. Char flag was always 0. So this will only look at the 0 flag because char flag is 0. I emulate this code, open the flags, and run. Char flag is always 0 and it is jumping. When the char flag, 0 flag was 1, the condition, this condition becomes false, so that it will not jump. Okay. So now I'm going to go over and look at the compare instruction. With the compare, we will combine the jumps and compare. Okay, compare instruction. Let me close these all, minimize this, close these ones. Compare instruction. As I said in Turkish, compare instruction is just a subtract operation. It subtract from first operand from subtract second operand from first operand. But the result is not stored anywhere. The most important part is here. The result is not stored anywhere. It just makes subtraction. The registers or memories are state that value isn't updated. The result is not stored anywhere. Let me copy this example, which is simple as I can see. L5, BL5, it is going to compare this AL and BL. Let me put some other value here in order not to stop the program at there. Okay. I'm going to open the flex also. Flex is important. Compare is only, we are only using compare for updating flex by subtract operation. Okay. AL is 5, BL is 5. 5 minus 5. This compare operation will execute this code. The result is 0, but the result is not stored anywhere. The flex is updated. When the result is 0, remember, CL becomes 0, 0 flag will set to 1. Now, the result is 0, and again, 0 flag will become 1. I'm going backward and forward for you to see the change in flex. Please look at the flex in here. Oops. There's also another flag which is updating. Parity flag. The result is, no, not the result. Parity flag means the number of elements in the result, number of ones in the result in binary. If the number of ones is even, it becomes 1. If the number of ones are odd, it becomes 0. Parity flag is this. The result is 0, so number of ones is 0. 0 means even. Okay, that's why parity flag becomes 1. But we are not interested in parity flag for now. We are working with 0 flag, char flag, and maybe sign flag for now. Okay, as you can see, it updates the 0 flag. So how we can use this one? For example, in the previous example, I write an endless loop. Remember, this is endless loop. It keeps doing something Let's make add operation. Add 1 into CL. It's just a meaningless operation. And again, oops, deck, not sub. This is endless loop. Remember, I'm going to emulate this and run this code so that you can see that this is endless loop. There's no condition that program can halt or exit out from that loop. So we can add a condition in here. CMP condition. I'm going to look at the CL value. For example, let me also add 1 to CL. We are updating CL 2 by 2, and I'm going to control if CL is, for example, 10 or not. I'm going to compare CL with 10. So operation is equal to CL minus 10. It will update some flags. According to those flags, we need to update jump. For example, no, let's not update this jump and use another jump condition in here. For example, we learned the jump equal GA. I created the end label. This is the inner block of loop. This is endless loop. Within this endless loop, it checks if CL becomes 10 or not. If it has become 10, the compare instruction will update the 0 flag with 1 so that jump equal, which was, go over and look at the jump equal, which was only looking the 0 flag. If 0 flag is 1, it will jump to the end. I'm going to emulate this code. Let me show CL is this. Okay. Please look at the CL value. CL is 4, CL is 6, CL is 8, CL is 10, and the program is finished. So I created a loop which is heavily depend on the value of CL. So this is not a predefined loop, but let's not use CL but AL. Complicated because loop, remember, using CX. Let's use another one with a single increment. Okay. I'm going to move AL3. Okay. For example, this is an exam question. Mesela arkadaşlar bu soru sınav sorusu. Bu loop kaç kere çalışır? This loop. How many times is this loop gonna work? How many iterations does this loop has? Ömer says 7. Any other idea? You will calculate. You can calculate. You have the emulator. You can even put a counter in here. For example. Use the bx value as a counter. Increment bx. At the end of this program, we can look at the bx value and see that how many times that this loop iterated. Run this code and looking at the bx value 3, 4, 5, 6, 7, and end. And Ömer, yes, it is 7. Thanks for your correct answer. Ve böylece arkadaşlar sınavda nasıl sorular soracağımı da anlamış olacaksınız. Mesela bu gördüğünüz basit. Yani size yaklaşık bir dakika vereceğim sınav sorusu. Bu loop kaç kere çalışır? This is an easy 1 minute exam question for you to understand and results. Yes, Utku, you can set your flags manually. This is also the topics of the next, for example, which one? Let me look at PDFs. For example, CLDs, STD. These are clear direction flag, set direction flag. Or you can directly look at the emulator. For example, setting carry flag. SDC. This is set carry flag. It updates carry flag to the 1. You can also use that also. For example, I can use SDC. It doesn't have any operand. By this way, let's use not STZ but ST0 flag. Any updation to 0 flag? No, you can't update 0 flag. Only carry flag. Direction flag. STI. Interoperable flag. There is no STZ. Why? There's no STZ. It's just carry flag, direction flag, interoperable flag. Okay. You can use different jumps which are looking at the carry flag. For example, JC. Jump if carry flag is 1. And use STC at there. But you got the idea. The compare operand make subtract operation, but the result is not stored anywhere. And after that, we can use the flags to jump to somewhere. For example, I put the end in here, but I can beginning start. This is a meaningless and endless loop. It runs 7 times and starts from the beginning. You don't have to go over and continue from forward. You can continue from backward also, because this is jump. Updates the instruction pointer to the backwards. Okay. So is there any question about compare? Compare operand, by the way, I didn't mention that. Different versions, memory immediate, register immediate, but also there's no memory. There's only memory immediate, register memory, memory register. We use register immediate, the last one. It can also be register, for example, this way. The result is not stored anywhere, it's not important. Compare instruction, as expected, updates all the flags, can update all the flags according to result. And that's it. Let's go and write the answers of these questions. Okay, is there any question? Let me ask again. I'm going over and diving into examples. If there's any question, please open your mic and say I have a question. Okay, question 1. Write a program that analyzes this memory address, and if value of this memory address is equal to C2, write FF into this memory address. If the value is not equal to C2, write AA. So this is simple if and else. If this memory address has the value of C2, write FF. Else, write AA. Normally, you write an if condition in C and check the 1000 address, and if it is equal to if equal to C2, it will going to update 1100H with what? FFH, 0 FFH. Else, it will update 1100H with what? AA, 0 AAH. This is the C code actually. The program wants you to emulate this code in assembly. Okay. Put mass. Okay. Now, before, let's put some value in the 1000 hash address, because the memory is always empty, it's all zeros. Let's put C2 at first. Let's say 1000 H address has the value of C2. Okay. Now the condition. We are going to check if 1000 H is equal to C2 or C2 or not. I'm going to use compare as an if. Compare 1000 H address with C2. This is the line that we are using. If this is true, if 1000 H is C2 like in this condition, the result will become 0, and I'm going to use a jump something. By the way, GCC is something. There's no GCC code. G, etc. as an indicator. There will be some J, and this code will run this code. If it is not, it will run this code, and the program will finish. Yeah, program will do that. So let's solve this problem. It compared with C2. This C2 becomes equal with 1000 hash. By this way, we can use 0 flag. The instructions that using 0 flags are JZ, or JE. Is there in JZ? Here, there is JZ. If 0 is 1, then jump. JE also, JE. JE is also, if 0 is 1, then jump. Let's use JZ. I'm going to put a true and false labels. If JZ is true, 0 flag is set, jump to true and run this code. It is not 0 flag. We are going to use the opposite version of this jump. which is jump not 0. If 0 flag is set, then jump. E false. Okay. So let's emulate this code first. This is wrong. We are going to correct this one by debugging. Okay, 1000H address now has the value of C2. Now I'm going to compare this C2 with C2. So the 0 flag becomes 0, becomes 1, because the result is 0. And jump 0. Jump 0 is jump if the 0 flag is 1. So 0 flag is 1, it is going to jump. It jumps into true case. Okay. I'm going to continue this code. And it's run the second case, false case. But I only want to run the true case. The false case must be jumped over and shouldn't be run. That's why after true case, I'm going to use jump to end. Let's say there is a label at the end. So this is the correct version of the program. C2, compare C2 with C2. 0 flag becomes 1. 0 flag becomes 1. It jumps. And after that, unconditional jump will go over to this block. This block didn't run. As you can see, it's over. Okay, so let's update this 1000H value with something different, AB. With this code, 1000H has the AB value, and I'm going to compare AB with C2, open flags. AB minus C2 becomes something, carry flag, 0 flag, sign flag. There are lots of flags updated. Sorry, carry flag and sign flag is updated because AB minus C2 is negative. AB is smaller than C2. Result is negative. This sign flag stating that result is negative. This carry flag is also the borrow flag. There is no borrow flag. Carry flag is also borrow flag. So it's stating that this, in order to calculate this subtract operation, we borrow a bit. This carry flag stating that. It's not important. We are not looking at those flags. We are only looking the 0 flag. So 0 flag is 0. JZ, which jumps when the 0 flag 1, will not going to jump and go over the next instruction. Next instruction is, remember, in assembly, instructions are run by next to next. It goes one by one. When 0 flag is not 1, it didn't jump. And the second instruction was jump not 0. 0 flag is 0. So this jump not 0 will jump into false part. Did you catch the idea? Jump into false part, and 1100 hash becomes AA. By this comparison, we know that 1000 hash value doesn't have the value of C2. Okay, but this is some garbage. There are lots of unnecessary codes in here. Let's make clarification in here. For example, in if-else block, it has to be run. One part of the if-else part has to be run. If this is true, this will be run. If this is false, this will be run. So one of them has to be run. Okay. So that's why before this compare or jump operation, I'm going to put one of these value directly into 1011 hash address, stating that 1000 address has the value of C2, but it is not correct. I just put it there, and I'm not going to use this part. I erase the first if part, and I'm going to delete this jump 0 part. Let's see what it is doing. It puts A, B, and FF into 1100H, FF, and checks if 1000H address is equal to C2 or not by subtracting AB from C2. It is not equal, so the result will not be 0. So we update this code with to AND. This is the false part, but we don't need the false label. Yeah. But we use the wrong version. Okay, let's emulate this code. We put AB into 1000H and directly putting one of the blocks in 1100H and compare this AB and C2. They are not equal, so it should write AA into there. So it didn't write AA, so we write the opposite version. Let's change this into the correct version. So this is the correct version of a simple answer to this program. It writes directly AA, stating that they are not equal, and after that compare the value with C2, and the comparements say that they are not equal, so that it will jump to AND, not instructed this instruction. Let's update 1000H with C2. You will see that it will put FF. First it put AA, and then after comparement it updates AA with FF. This is the correct version. 1000H has the value of C2, and the address of 1100 becomes FF. This is more clarified version. We use jump not 0. It's up to you. You are going to find an instruction for your use case. For example, jump 0 and jump equal are same. GE and GZ are same. The only difference are the signed unsigned part. As I said earlier, there's a documentation tutorial about these jumps. Let me show you the jumps. Unconditional jump. Okay, short conditional jumps. For example, as you can see, these are same. They are in the same line. And opposite instructions are here. Okay, the title states that the below tables are instructions that test single flag. As you can see, these all jumps looks only for a single flag. Jump instruction for signed numbers, jump instruction for unsigned numbers. Okay, if you are going to work with unsigned numbers, be careful about the jump you are going to use, because not all jumps are same. For example, GG, which means jump greater. Jump if greater than things, but we have also GA, jump above. This is also looking at the same thing, but one of them is unsigned, which is GA. GG is signed. So you have to be careful if you are going to work with unsigned numbers. Okay, this is in the tutorial section, program flow part. Okay, I'm going to ask this in the exam. I warn you. Okay, jump 0. And let's go over the second question. Let's say the memory has these blocks. I'm going to copy. And I'm going to explain these byte PTR things later. Question saying that from starting from 1000H address, there are some values like 12, 13, etc. There are some values, but we don't know how many numbers are there. We only know that the end of this array has an element of 0. This is an array of bytes written on memory beginning from 1000H with an ending byte value of 00. We only know that the last element is 0. We didn't know how many elements in here. So we need to write a loop. For example, if I write a loop by using loop keyword, I have to predefine the CX value and how many times this loop should run, I have to predefine. For example, 7, etc. But we don't know. This is the memory. No, we don't know yet. We don't know how many elements are there in the memory or are there in this array. So I'm going to use an endless loop in here. Jump something loop or JMP loop. This loop will do the instruction and check if the last element came or not. Copy this array memory from 2000H. Okay, we get the value from 1000H. Check. Let's write it directly. Get the 1000H address value from the memory. Make comparement if it is 0 or not. If it is 0, it means the array is finished, so the program should halt. So I'm going to use the jump equal. We're not unconditional jump. By the way, I have to move this value into 2000H memory address. Okay, just this value into 2000H memory address, and after that make comparisons. Okay, after this operation, the program finish. But it starts from 1000H and needs to be incremented by 1. So I'm going to use source index, one of the index operator. Let me use source index and use source index in here. I have to increment source index after move operation. Yeah. Let me emulate this code. It puts some value into memory let's go and look at the values. 1, 2, 3, 4, 5, 6, 7 goes like that. The values are like here. I'm using source index and gathering the first element. For example, AL becomes 12. And get this value into, oh, you should put this value into 2000 memory address. Okay, now we have to use destination index or a constant value. Let me show you the new keyword, echo, equal. Let me say 1000, Turkish, or 1000, 1000H. And I'm going to put 1000 here. Let me emulate this code. Long parameters because there's no semicolon. Illegal instruction. I forget something important. Let me check that. Oh, the opposite one. Not this way, this is beforehand. Like we see in here, and there's no semicolon, comma. Okay, 1000 becomes 1000, and this is the correct one. This I becomes things. Let's go over and look at 2000. Yep. Okay. Now let me explain the things that we use today. We can define constant values, like in C, there are constants. In assembly, there are also constants. In here, with the equal keyword, you can define constant variable. I use 1000 as a keyword and say that it is 1000H. And I use that before the parenthesis. And the resolution of this parenthesis become 1000H plus source index, which is also 1000H. So the result becomes 2000H. Okay? By this way, we can use constant value and not use another destination index. So we are getting value from 1000H and putting it into 2000H and increment source index. It's now 1001, and we are going to compare the AL value, which is the previous 1000H, with 00. If AL is 00, then it will set to 0 flag. If it is not, the 0 flag will be 0. So this jump equal operation will only look for the 0 flag. If the 0 flag is 1, it will jump. If it is not, it will not jump. So the point is this. There are some values in the memories. We only know that the last element is 0, 0. And we make a loop in here. We don't know how many elements are there. Let's say we don't know. We use like this. We don't know how many elements are there. We only know that the last element is 0. And we keep copying these elements into 2000H address. So this is basically creating a new array and copying the old array into new array. In C, create a new array and copy it into previous one. That's it. So the new usage of constant is with equal. I don't use it that much. We use compare element with jump equal. Okay, now there is also another new thing, byte PTR. Byte PTR means, please remember, move AX1. Remember this code. When we emulate this code, the machine translates this value into 00001H. Okay, because I use AX, 16-bit value. Now I'm going to use AH, 8-bit value, and the machine translates this into 01. So the emulator needs to find a size, either from the first operand or from the second operand. Okay? For example, if I didn't write anything before this 1000H value, the first operand didn't state a size. It's just a pointer pointing the 1000H address. And the second operand didn't also stating a size. It can be 0012 or 12. It didn't state a size. That's why we put byte PTR before this parenthesis, so that we are saying to emulator that we are going to use only the byte part of this 1000H with operand 1. With operand 1, we are saying that this instruction will work with byte. I'm going to write the different version. There is also word PTR. Let me use 12 again. We use word PTR, the 11th line. As you can see, it understands the size of the first operand from the word PTR and copy the value of 00012H. Okay? If I use byte PTR, it will copy the 012H. So this is only forcing emulator to use only byte. We can, for example, I'm going to use word in here. Not here, but the second one. Part. Let me use word in here and emulate this code. I emulate the memory part and go over and look at the memory. 1, 2, 3, 4, 5, 6. It updates after that, so that it's not using. Let me use word everywhere. I can't find a proper example to show you the importance of word or byte. How can I determine? Let me use word in here and put one value like this. For example, 12AA is a word. It puts into one starting from 1000H address and put into memory as a AA12. But after that line, we update the 1001, this line, this 12 line with 34. And go over and look at the 1000. As you can see, it becomes AA34. The 12 is lost because the lower part is in 1000H address, the higher part is in the 1001 address, and 1001 address is updated in the next instruction, so 12 is lost. So be careful. It's important to state the size. By the way, this is wrong usage, I think, because you can't put word in bytes. It gives error. Okay. Any question about this example? Any question? Anything you don't understand? We can use DA, DI, but we have to increment both of them. For example, 2000H, we can use DI and also increment DI. This is also true. But there's also another thing. Let me use that again. BX. BX is the only register can be put into parentheses. You can't put AX in here, but you can put BX in here. Okay? So I'm going to use BX. I'm not going to use DI. Okay. Let's increment BX. I use source index plus BX, not BC, BX. This is also true, but we have to put a value into BX. Let's put 0 at the beginning. So this is the 1000H address because SI is 1000, BX is 0. The result becomes 1000H. This is also 1000H. Incrementing BX will increment 2 into 1001. Oh, this is wrong. We have to put this into 2000H address. So how we are going to do that? X is a 1000 and index is a 0. Use BX in here. No, it should be 1002. Yeah, 1000, 2000. That's it. Any other question? Let me show you the tutorial part of this BX memory. Open that up again. Tutorial memory access. Yep. Within the parentheses, as I stated, you can use source index, destination index, and only BX. We can also use base pointer. We will cover that in the next weeks. Know that we only use BX for now. Any other question? I'm going over to next example. My camera just stuck. Okay, let's go and look at the next example. Write to memory address between 1500H and 1500 FFH. Between these values, hex values that began from 0 and increase 1 to FFH value if corresponding memory byte values equal to 0. It's saying that there is a memory range. We are going to put values starting from 0, increased by 1, if the memory is empty. So let's write this code. We are going to use 1000H and 1000 FFH memory range. So I need to check if the memory is empty, which means 0. I need a loop. This time loop is predefined. It will run how many times? Who can say that? How many times this loop needs to run? This loop is predefined value. And what is the CX value? Any guess? What will be the CX value? How many times cover this range? Bytes value. As you can see, this time it's not word, it's byte. FFH. Thanks, Ömer. It's FFH. This loop needs to run FFH times, and it needs to check if the memory of hash is 0 or not. If it is 0, if it is not 0, jump. If it is 0, jump. Let's say jump equal to. If it is 0, jump not 0. If not 0, the program will finish to end. Sorry, this will be like this. If the memory location is not 0, it will jump and program will finish. Is it stating that hex value that began from 0 and increase 1 to FF value if corresponding map value is equal to 0, 0? It is not stated explicitly, so this is a bit complicated. This is wrong examples, just not stated everything clearly. Just know that if there is a memory is not empty, we halt the program. So this is the code. We check the 1500H value with 0. If it is 0, it will copy some value like we have to start from 1. We have to start from 0 or 1. 0. We have to start from 0 and put this AL value into $5,000 address. Yeah. After that, we need to increment AL. This is the loop part. We look at the memory location. If it is 0, we put AL into there. And we need to increase this 1500. That's why I'm going to use source index in here. Hash. Source index here. This time destination index will be more meaningful, by the way, but let's not use that. We also need to increase by 1 source index. Yep, this is the code. Let's emulate this a little bit. Stop at some point and go over and look at the 11 part. 0, 1, 2, 3, 4 goes like that. 5, 6. Yeah. So this is the code. There can be optimization. For example, I'm going to use BL, BX, not BL. And I'm going to use BX in here. BX is 0. Put there. Only increment BX. This is also doing the same thing. So 3, 4, 5, 7. And let's put some value at the position of 1015, let's say 5 H address, some value in there, like 11H or AAH, so that the program will halt there. Oops, something's not true. What is the problem? Reload, put some value into 5000. 5. Oh. There are already values in the memory. Yep, this is more correct one. And run. It is not working. Why? When we emulate this, okay, CX is FF, CI is 1500 plus BX. BX is 0. Increment BX, jump not 0. Let's open the flags. Look at the 0 flag. It is 0. So it will not going to jump. Okay. Source index is 500, Bx is 0. Bx is increased, Bx is now 1. So this will result into 1001. It's again 0. When the Bx become 5, Bx is now 5. This compare operation should not set the 0 flag. Why there is a problem? Because we put AA and make compare operation, AA minus 0, 0. Let's go over and look at the jump not 0 instruction. Is there any catch we can't use? Jump not 0. Short jump if not 0, set by JMP sub at test and or it can be set with, yep, jump not 0 label 1. Oops. Oh, sorry, I closed the example altogether. Let me open the answer then. I don't like this answer, but this is the data segment part. This is the loop. Constant value 5000, and we use source index as a constant value. It didn't finish the program. We tried to finish the program. FFH. Ondan mı? Niye daha önce söylemediniz gençler? Programı kapatmış bulundum. Neyse. Let me finish this example by this answer. Within this range, we try to copy the incremented value into memory if the memory is empty. If it is not empty, this is not the correct answer. There's a loop. Loop runs FF 400H times. No, this is not the correct answer. let me write again. I write this way, not using constant value. I use BL, yes, putting BL into, but before that I need to make compare operation. Compare this value with 0, 0, okay. Do we have to say byte PTR in here? Let's say 0, 0 hash. Using jump not 0 to end. Putting BL into this address, increment BL. Oops. Get this, and by the way, we put AH. Okay. Now we put some value into 5. Yes. We start from here. When it comes to 5, it will finish the program. Let's run this. Yeah, this time it finished. What was the error we were getting? I couldn't understand, but this is the correct one. Ömer and Utku catch something. Anyway, if the memory location is empty, which means 0, it will jump to the end. If it is not, it will not jump and copy that value into memory location. Let's comment out the first line and see the memory. CX. Finally. One, two, three, four, five, six, seven, A, B, C, D, E, F, and goes like that. If there is any thing in, for example, in A address, it will only run 10 times. I think this address is painful. Okay, 1, 2, 3, and A in the A address. Okay, any question? No, it doesn't matter. FF plus 1, 100H. We are starting from 0 and going to till FFH, so the correct version is 100H, not FFH. Any question? So we use compare operand, some jumps, loops, and base pointers, and even, not in here, but in here, even use the equal operand, constant definition. We can use constant before this parenthesis. Yep, that's it. Any question? İşte ekranı yanlışlıkla kapatmasaydım çözerdik büyük ihtimal Ömer de. Ekranı kapatınca gitti. Kayıttan bakarsınız. Sonra. ZF1 olmasına rağmen atlamayın. Çünkü ZF hep 1 oluyordu. 1 olmaması lazımdı. Oraya A koymuştuk. Muharrem Hocam,
Abbas hocam teşekkür ederim anlatımınız
Ben
için.
teşekkür ederim.
Arkadaşlar katıldığınız için teşekkür ederim. Bir soru var mı?
Ben Türkçe olarak cevaplamaya çalışıyorum hocam. Sadece kaydı
Tamam.
durdurursanız iyi olur.
Ben kaydı durduruyorum. Teşekkürler hocam. Dilinize sağlık.
Sağ olun hocam.